digging into some really fascinating ideas you sent over, this whole concept of universality, how simple ideas can suddenly have this, well, infinite reach.
That's right. It's about how different systems, we're talking writing, computation, even life itself, seem to make this jump from being useful for one thing to potentially being able to do almost anything. It's quite a leap.
Exactly. So we're going to unpack some key examples, look for those moments where things, shifted, connect some dots. The material is great. Takes us from the very first drawings for words.
Pictograms, yeah.
Right, pictograms, all the way to thinking about infinity and what that means for, like, the real world.
And the main thread here is this jump to universality. What does that actually mean? And why wasn't it usually the goal? It often seems like an accident, almost. We want to understand what that implies for knowledge, for problem solving. It's a big picture.
Okay, let's start way back. The dawn of writing. Your sources talk about those early pictographic systems.
Yeah, where a symbol basically just stood for a word or an idea, like drawing a sun for sun. Pretty direct.
And they were used for specific things, right? Like keeping track of goods, that sort of thing.
Exactly. Administrative tools, mostly. The goal wasn't, to write down everything people could say.
Which makes sense. Imagine needing a unique picture for every single word. It'd be impossible. But then comes the first hint, right? Using sequences of pictures. The source had that hypothetical English example. Tree plus sun, meaning treason.
Right. And what's key there is the rule. Combining existing symbols creates new meaning. Suddenly, the system has more reach. It can represent words that weren't explicitly drawn before. It's combinatorial.
Like musical notes, yeah. A few notes, endless melodies. And the source points out this mirrors language itself, words built from basic sounds.
Precisely. Which leads to this next big step, potentially representing any word. And the source gives that clever idea. What if the pictures stood for the initial sound of a word? So treason becomes tent, rock, eagle, zebra, nose pictures. That's the principle behind the alphabet. That's the universal jump for writing.
And that's where it gets really interesting. Universality through rules, not just a massive list of symbols.
Exactly. The rules are way simpler than memorizing thousands of pictures. And because the rules tap into that underlying structure, the sounds, they actually hold more knowledge about the language.
So an alphabet lets you represent existing words, but also, crucially, coin new ones easily.
Yeah, completely decentralized.
Yeah.
Need a new word. Just combine the sounds. No need for a committee to approve a new picture.
But then the puzzle. If alphabets were so powerful, why didn't everyone adopt them immediately? They seem stuck in specialized uses for ages.
Well, there are theories. Maybe scribes liked their jobs, made it harder for others. But perhaps, as the source suggests, people just didn't get the full implications of universality back then.
Like they stumbled onto the superpower, but were just focused on the immediate task, recording stuff.
That seems to be a recurring theme, doesn't it? The jump to universality often being this accidental byproduct of solving some other problem.
Okay, so that's writing. Let's pivot to numbers, another fundamental area. Tally marks evolving into universal numerals. Same pattern.
Very similar, yes. Tally marks are basic, right? One mark, one thing. Universal for simple counting.
But terrible for anything complex. Adding big numbers with just tally marks, forget it.
Absolutely useless for that. So improvements came along. Grouping marks. Then symbols for groups like the Roman numerals I, V, X, L, C, D, M.
Again, solving specific problems, making things a bit easier. Doesn't seem like they were aiming for, the ultimate number system.
Probably not. But their rules, like placing symbols side by side to add values, did allow something new. You could do arithmetic on the symbols themselves. The source shows adding 7 and 8.
Right, you combine them VII, V3, then apply the rules, group the V's into an X, the I's, and you get XV, 15.
Exactly. The system itself, through its rules, performs the calculation. The person just follows the steps. It's a conceptual advance over just tallying.
But still limited, right? The Romans didn't have symbols for really huge numbers. Beyond M1000, they kind of had to repeat it, like tallying again.
Pretty much. It hit a wall. Which brings us to the Indian positional system. Digits 0 to 9.
And the value depends on the position. That's the key.
That and 0. The placeholder. That's the absolute genius of it. Distinguishing 2 from 20 or 204, 0 makes it work.
That's the truly universal system for numerals.
It is. The source mentions the Babylonians had a positional system earlier, base 60, but it was clunky, and crucially lacked a clear 0 initially. Suggests universality wasn't the primary design goal there either.
It's wild to think of someone like Archimedes trying to count grains of sand.
billions upon billions.
And yet his system wasn't quite universal. He put limits on it.
Seems so. Laplace apparently marveled that minds like Archimedes missed the simple elegance of the Indian system. Was it just not thinking that way, or maybe a philosophical resistance to purely abstract numbers? Hard to say.
Again, focused on the immediate problem, maybe missed the bigger picture, the universal potential.
Then the sources shift gears a bit to the Enlightenment.
Right, a different attitude emerges. People start deliberately seeking universality, not just in science, but in things like justice, morality.
And in technology, too. Look at movable type printing.
Ah, yes. From carving a whole page as one block.
To having individual reusable letters. That's a universal toolkit for printing.
Didn't catch on as much in China initially because of their character system.
Right, thousands of characters. But in Europe, with alphabets, revolutionary. It's that same pattern. Specialized object for each task versus customizing a universal object, like the printing press, or later, the Jacquard loom.
Weaving patterns with punched cards, universal input leads us nicely into computation, doesn't it?
Absolutely. Charles Babbage.
Yeah.
His difference engine.
Designed for a very specific, kind of dull job, right? Calculating mathematical tables.
Seems parochial, yes, but mathematically. Because of Taylor's theorem approximating functions with polynomials, it was actually universal for a whole class of functions. Unexpected reach again.
And his printer for it used movable type. That universality pops up again. But his real leap was the analytical engine concept.
Oh, definitely. Programmable, using those punch cards from the looms. A universal classical computer in the 1830s.
The potential he saw was staggering. Arithmetic, algebra, chess, music, images.
A universal simulator, basically, predicting things. It's mind-blowing.
And tragic it wasn't built. The source mentions maybe using electrical relays.
Imagine. The computer age, maybe the internet, a century earlier. It's a huge what if.
Babbage and Ada Lovelace even thought about AI. Lovelace's famous objection.
That the machine couldn't originate anything, only do what it's told.
Which Turing later addressed. But the source suggests maybe she didn't fully grasp the potential universality of physics itself, that the brain could potentially be simulated.
It's complex. Searle's arguments later echo some of this, comparing brains to machines. But the key difference with a universal computer is its scope of simulation. Way beyond a steam engine.
And it connects to some modern AI debates too, doesn't it? Reductionism versus emergence.
It does seem related, yes. Underestimating how complex behavior can arise from simple computational rules.
So Babbage didn't build it. Took almost a century until World War II for working universal computers.
Driven by urgent needs, code breaking, ballistics. But because they were universal, they could then do anything else. Spreadsheets, games, astrophysics.
It's amazing. The chip in my washing machine, theoretically, has the same fundamental computational power as ENIAC, just faster and smaller.
In terms of the repertoire of possible computations, yes, they're equivalent at that core level. Babbage's engine, ENIAC, your laptop, all universal Turing machines, essentially.
And they're all digital. The source makes a point about analog computers getting left behind.
Because of error correction. That's crucial. For complex, long computations, you need to fix errors reliably.
Ah, okay. Analog struggles with that. Continuous values drifting.
Exactly. Errors accumulate without easy correction. Digital systems, with their discrete states like Babbage's gears clicking into place, make error detection and correction feasible.
So error correction is almost like a prerequisite for this beginning of infinity in information. You need stability to build complexity reliably.
That's the argument. It allows knowledge to accumulate without being constantly degraded by noise. It might explain why these universal jumps often happen in digital-like systems, discrete sounds, letters, numbers, binary states.
Okay, now for maybe the most profound example the source brings up, the genetic code, DNA.
Yes. This code evolved, presumably, for very simple early life. Single cells, maybe. And yet, it's the blueprint for everything. Bacteria, whales, us.
It's staggering. A language that described organisms with no nerves, no limbs, no eyes.
Now specifies brains capable of contemplating the universe, complex behaviors, everything.
The mystery the source points out. Early on, the code itself seemed to evolve to allow new biology. New knowledge needed new code variations. But then, the code itself basically stopped evolving, yet its reach exploded. What universality did it achieve?
The suggestion is maybe a kind of universal constructor capability. The ability to build almost anything complex, from simple materials, following instructions, even programming organisms to build things externally. The fact DNA can be used for computation, like Adelman showed, hints at this latent power.
Which connects back to us, right? Humans as universal explainers. Maybe that's the ultimate physical universality we know.
And if we achieve true artificial general intelligence, the source suggests it won't be just a clever program, it'll be a person in that sense, a general purpose explainer.
Wow. Okay. Deep breath. We're heading into infinity now. Abstract, counterintuitive.
Definitely. Maths handles infinity fine, infinite sets, infinitesimals. It's just our everyday intuition that struggles. And this idea, the beginning of infinity, unlimited knowledge growth, relies on these mathematical infinities being consistent.
The source tackles finitism, the idea that only finite things are real. But it hits problems like, is there a biggest number? Seems tricky.
Yeah, the argument is that finitism is kind of anti-explanation. It's anthropocentric, limiting maths to what we can easily grasp. But our grasp of finite is pretty limited itself.
And rejecting infinity, it argues, ultimately limits reason, forces you into parochial thinking or maybe even the supernatural to explain things.
Cantor really founded the modern study of infinity. His principle, define abstract things consistently, even if they feel weird. His ideas weren't popular at first.
Hilbert's Infinity Hotel. Love that thought experiment.
It's brilliant, isn't it? Shows how weird infinite sets are. Always room for more guests, even when full.
And Cantor's diagonal argument, proving some infinities are bigger than others. Real numbers versus natural numbers. Mind-bending.
Truly profound. Uncountable infinities, it changed mathematics.
The source uses the Infinity Hotel again for those weirder thought experiments. Trash disposal, puppy annihilation. Sounds grim.
Huh, yeah. The point is, actions that seem reversible in a finite world can have irreversible consequences or lead to paradoxes in infinite systems. Things go wrong.
It messes with intuition about probability, too, right? What's typical or rare in an infinite set.
Which impacts things like anthropic arguments about the multiverse. If it's infinite, you can relabel universes to make fine-tuning look common or rare. Probability breaks down without something more.
A physical measure, like interactions between universes giving them some relative weighting.
Something like that. Maybe quantum theory provides a basis, the source speculates. You need physics to ground the maths when talking about reality.
So distinguish the mathematical definition of infinity, one-to-one correspondence, from just really big. Don't confuse maths with physics.
Exactly. Physics tells us what's finite in nature, resolves Zeno's paradoxes. Geometry evolving from pure math to Einstein's physical theory is a key example.
Proofs and computations are physical processes modeling abstract ideas.
Which brings us back to Turing and Gödel. Non-computable functions, unprovable truths. Why? Because there are more possible functions truths, uncountable, than possible programs proofs, countable.
So our knowledge of math depends on our knowledge of physics being reliable.
In a way, yes. It's all intertwined. The unreasonable effectiveness of mathematics Wigner talked about. The laws of physics seem unusually computation-friendly. Anthropic arguments alone don't seem to cut it as an explanation.
And explanations putting computation before physics, like we're all in a simulation, the source seems skeptical, leads to infinite regress issues.
It tends to, yeah. The source concludes more optimistically, though, that interesting problems in maths, science, philosophy tend to be soluble. Uninteresting ones often aren't, which is why they don't hold our attention. The distinction is objective in the long run.
The biggest limit on knowledge isn't insolubility, but just that we can't predict future ideas, which is actually because knowledge growth is potentially unlimited.
Right. Problems are soluble means progress doesn't require magic or violating physics. Not that we have all the answers now.
Wow. Okay, what a journey. That was a real deep dive into universality. From ancient tally marks to the structure of the cosmos and knowledge itself. Your sources really tied together some incredible threads.
It's fascinating, isn't it? How solving one small problem can accidentally unlock this vast unforeseen potential, and how our understanding of abstract things like infinity is so deeply connected to the actual physical laws out there.
It really makes you think. The rules of the universe shaping what we can even know or compute. What other leaps to universality might be waiting just around the corner? In AI, maybe, or somewhere else entirely?
It's a great question. Hopefully this gives everyone a new lens to look at, well, progress, discovery, the limits and potential of understanding. What stood out most to you in all this? What new questions pop up?
So much to think about. Thanks for bringing these sources to us. Really, really thought-provoking stuff. We're already looking forward to whatever you send us next time. Until then, keep exploring.